Hi, I'm Jeff McCartney. I'm going to talk about natural language processing and then also talk through the aspects of NLP along with some of the algorithms that they use to do NLP processing. And then I'm going to talk a little bit about deep learning and how it relates to NLP. So the first thing I want to discuss is NLP in general and what its purpose is. So there's a lot of documentation out there, a lot of Word docs that describe things, describe events, describe activities of companies, describe all kinds of stuff. We try to communicate through words the best we can as humans, and while it's easy for us to communicate that way, it's not very easy for computers to understand that communication. So NLP's goal is try to convert that document into something that is more meaningful to a computer. And in our example case on the slide is we have our Word document, and then we extract the who, the where, and the when from this document. And in this test case, we're going to be talking about Bob Dylan is going to have a concert at the Red Rocks on June 9th. And that is the goal or purpose of NLP, is to break it down into something that the computer can understand. And so we have a bunch of steps for NLP to work, and I'm going to go through each one of these in a bit of detail, talk about their process and the algorithm that they use to perform their task. And for the first one, we have tokenizing. And tokenizing is taking a sentence and breaking it up into words and sentences, or a body of text, I guess, because we're going to have more than one sentence per document. And in our little scenario, we have Bob Dylan is playing at the Red Rocks June 9th. So we can identify spaces, and for each character that leads up to a space, we can say the preceding characters are, since the last space we saw, is a word. And then we parse that sentence in character by character until we get to the end, and we see a punctuation, whether it be an exclamation point, a question mark, or in this case a period. And we say everything we saw since the last punctuation is our sentence. And these if-then statements that we have below, those are rules, if-then rules. If this, we'll do that. And in this simple scenario, if we see a white space, what we saw previously is a word. And then also for the sentence. So we break up this entire document into a bunch of sentences and a bunch of words, and now we have at least some idea of what's going on from a computer perspective, because now we've tagged it into a higher level of meaning. So the next step takes that higher level, those words, those sentences, and we say, well, let's try and figure out the parts of speech. So we go word by word again for each sentence, saying, what part of speech is this? We can use rules to determine that. We can use hidden Markov models to determine that, or we can use ontologies. So the rule approach is basically, Bob, 9 times out of 10, when we see this word, it's a noun, proper noun, and, is a verb, and playing is an adverb, etc., etc. And we can create lookup tables and if statements that say if it's in this lookup table, then it probably is this part of speech. And we could say if this word follows a previously seen word, then we know that it's that part of speech. Hidden Markov model is an optimization into a graph to say that progressively as we see these words, these are the parts of speech these words are based on what we saw as it traverses through the graph. Hidden Markov models are the accepted approach to solving this particular problem. But another approach is using an ontology, which is a tree. So instead of a graph, now we have a tree. And that tree, as we progress again through that tree, it highlights, or it results, each end node results in what part of speech that word belongs to. And once we have all this information, we can now move on to the next step. And the next step is what's considered entity recognition. I prefer to call it the concepts within the document. So in our little test case, Bob Dylan is not only who this document is talking about, but it's also a person, it's also a famous person, it's also a name, a first and a last name. So we have all these contexts or concepts. Sorry, let me use my correct term. We have a lot of concepts that these two words relate to, and so we need to be able to apply these concepts to these two words, and we know that because of what we've built before. So we now know that Bob is a word, but it's also a noun. It's also a proper noun if we've gone that far in the parts of speech. I got allergies. So Bob Dylan, or Bob, has all these other tags that we've seen before. And based on these tags, we can now create an if rule that says if Bob is a noun, is a proper noun, and is in this word list of names, we can say it's a name. Now we can create a rule that says, well, Bob is a name, and it's followed by a name. So Bob Dylan, or Dylan, is classified as a noun, a proper noun, and now we've created a rule to classify it as a name as well. And so now we create another rule that says if it's a name followed by a name, then it must be first and last name, given this specific domain, because we have other domains, like the Japanese language, that they put their family name first and then their personal name second, individual name second. And then we can also say, well, it's contained within this sentence, so we know that Bob Dylan is the Who, and he's going to Red Rocks, and he's going on July 9th. So we've already bubbled up Red Rocks to a location. We've already bubbled up June 9th to a time or a date, based on our rule logic, lookup tables, and also comparing where it's at within the sentence, and also based on what part of speech it is. So these all combine in these rules to be able to allow us to bubble it up to a high level concept. Now they also use ontologies to do the same work, and of course again it's just branching within a tree structure as we go through the words that we're looking at, and the branches gets us to the answer that we're looking for, the who, where, and when concepts. There's another aspect of natural language processing, and that's co-referencing. Most of the time I've seen this implemented, or let's talk about what it is first. So co-referencing is when you have a pronoun that's referring to an actual noun somewhere. So he, this, that, it, she, her, him, etc. are referencing something previously stated in the document. And co-referencing tries to identify that. In reality, what it's probably going to result in is actually a replace of, in this simple case, Bob Dylan will replace he, and so the computer will see Bob Dylan is the famous musician instead of he, so it doesn't know, so it's not in a state of cluelessness and trying to understand what he is representing. This is generally implemented with a rule engine, so you have your entity tagging, and then once you have all those tags in the document, it can go to each pronoun and then reverse look up in the text until it finds the proper noun that it's referring to. But then once we have all these high-level concepts, we need to extract them out of the document, put them into a database of some kind, or a table of some kind at least. And then we have, for example, now we have Korn is playing in Denver, July 10th. And we need to say that, or our ultimate goal is that we want to only send events that our end user is interested in. And we need to be able to discern which events are which. Just having, Bob Dylan, Red Rocks, June 9th doesn't really mean anything from a computer perspective. So how do we get it to understand that these are different? And the current approach is using a neural network. You have these 3 data points, and you feed them into the neural network, and it identifies that Bob Dylan at Red Rocks June 9th is a unique event, Korn is a unique event, and then you want to say that, well, even though Bob Dylan at Red Rocks on June 9th is a unique event, we still want to capture other events that Bob Dylan is at. Maybe we want to constrain it to an area, so all of Colorado, instead of just Red Rocks or just Denver. So we want to expand that and have it be a little fuzzier and say, well, we want all Bob Dylan in a given region or a given state in the United States instead of just one specific venue. And so we create the neural network, we feed it all these results, and we direct it to understanding that Bob Dylan is the most important piece of information, and then the secondary stuff, and it starts to group through training backpropagation, i.e. we give it the value we expect to see when we give it a certain set of inputs, and it'll reset its link weights to train itself, and that training will then allow it to be applied to newer values being supplied that are similar. And so once we have that, now we have a representational value of what we're looking at. So when we see Bob Dylan, Red Rocks, June 9th, the neural network gave it a 95% score. And when we see Korn in Denver, it gave it a 34% score because we don't care as much about Korn. And then we just create some simple code that just checks for this at a given threshold. If it's above 86%, then we expect the user to like that concert, and we send out an email to that user. And then we can add on top of that, and the user actually provides feedback and says, well, I don't like Bob Dylan, I actually like Korn. And so that feedback will then be applied to the neural network training, and it'll slowly shift back over to corn being the higher percentage and Bob Dylan being the lower percentage. And that right there is our workflow for natural language processing. This would be considered a complete solution to taking all the concert events, parsing them into a data set, and then based on that data set figuring out which values are important to our end user, and then sending an email to that user about that event. There is another approach to this process which is emerging, and that's called deep learning. Given the steps that we have for natural language processing, how does deep learning change the algorithms that are being used currently for natural language processing? Well, basically, it replaces everything in each step. It replaces all the algorithms and converts them into neural networks. Now you might be thinking, well, is it just one giant neural network? No, it's actually a bunch of small neural networks. So for example, tokenizing, we would have a neural network to identify sentences, and we'd have a neural network to identify words. And then for parts of speech, we will have a bunch of networks for nouns, pronouns, and verbs and adjectives, etc. And then we'll have a bunch for entity recognition, and each layer of neural networks, the results of those neural networks will be feeding into the next layer of neural networks. Okay, so those results feed into the next layer, which feed into the next layer, until we get to the top layer, which is extracting the high-level concept. And those results from all the previous layers are now combined and being fed into this top layer. And once again, we're not actually perceiving it as these like entity recognition. We're not seeing it as people. We're not seeing it as places. We're just seeing a value associated with it. The neural network doesn't actually know what it is, but it's assigning it a unique value so that it can be processed by the next layer of networks. And then once we get to the high-level concept, the high-level concept neural network will spit out a number representing what it is, and we'll need to have some kind of logic that'll translate that number into an actual meaning. So we'll say, well, 42. Okay, well, what is 42? I don't know what 42 is. Okay, well, let's see what the input was. Well, our input is Bob Dylan is going to Red Rocks July 9th. And so now we know that 42 is a representation of that. So when we see 42, our rule logic needs to send out an email about that subject. So that's deep learning in a nutshell. Still studying it, so my understanding is still high level as opposed to a deep understanding. So let's talk about our limitations on what these algorithms are constrained by. And the biggest one across all of them, or both of them, is it requires a human to provide its knowledge, or their knowledge. So you still need I mean, through NLP, you saw every step that is a bunch of if-then statements. It's an ontology with a tree structure that somebody has to create. It's the hidden Markov models that need to be trained to understand what the results need to be. And then ultimately the neural network needs to be trained to understand which data set is important and which data set is not important. It all requires human knowledge. I mean, even the neural network itself needs to be constructed in a way that it can understand what these data points are. You know, does it have 3 data points? Does it need 10 data points as input into the network? Does the neural network have multiple outputs, or does it have one output? What's the expected results of a given set of inputs? Requires a lot of human interaction to get these things, to know what they're processing. Even with deep learning, you're still sitting there trying to make sure that each layer, each network is providing a unique answer that understands or that makes sure that it understands what it's looking at, as opposed to it's just spitting out a random number and that number changes every time it sees the same input. You don't want that to happen. You want to make sure it's consistent, and you want to make sure it's distinct and unique. And so there's a lot of massaging, a lot of manipulating, a lot of managing these algorithms to make sure that they are capturing the information that people want to capture. The other issue is that these things only currently work against one domain. I can't spend all this effort pouring in all this knowledge and then hope that it can recognize a different domain. As soon as you say Red Rocks, are we referring to a place in Colorado? Are we referring to rocks that are red? Are we referring to something else? So as soon as you cross out of a domain, the meaning of the words become different. And how do you cope with that? How do you deal with that? And so that's another limitation that these algorithms have to deal with. And the last one that they have to deal with is a big one, and that's computationally intensive. These algorithms require lots of computers. There's workarounds, not just using a desktop CPU, but using a GPU. But GPUs use a lot of electricity. And then you have the other approach, which is using FPGA. Those are hard to program. And then you have using an ASIC, which is a permanently etched processor to do a specific task, so it's not very flexible. So if you screw up, you gotta burn a new chip. And so there's a bunch of limitations that the industry is trying to work through. There's a company out there called D-Wave that's trying to create a quantum computer that simulates how a neural network works. It's not exactly like a neural network. It's similar to how a neural network works, but it can potentially increase the performance of a neural network significantly. And they claim like 1,000-fold or something, but it takes a lot of work and handcrafting again to make that hardware perform at its best. So there's a lot of limitations to these algorithms. How are we going to move past them? Where are we going to go from now to get to somewhere where these algorithms can overcome these limitations? How can it learn on its own? How can it actually be just given a random set of inputs and say, I can see a distinct pattern, I can see a distinct feature, I know what that is, I've seen it before, or I haven't seen it before, I need to pay attention and learn what it is so I know what it is. How does it learn on its own? And then of course, once we can get it to learn on its own, how can we adapt it to other domains? Well, hopefully, if it can learn on its own, well, it can learn multiple domains. It can say, well, I can recognize this high-level domain, and that allows me to know that these words that I've seen before aren't meaning what they mean in that domain, they mean what they mean in this domain. And then, of course, how does it respond to dramatic changes in its current domain? Again, if it's learning on its own, it'll say, well, I haven't seen that situation before, those combination of values before, so I can now learn those combination of values and store them as a pattern in my brain. And I can say, next time I see them, I'll know what they are. And that's like the first step. There's a lot more steps beyond that, and I have an algorithm that solves that specific problem, but I want to talk about that in a later future video. And so I'm going to close this conversation for now. I hope you enjoyed it and maybe learned something, maybe not, maybe. But if you have comments or questions, please leave them below. And if you like this video, click the like button. And I think that's all I got. So until next time, thanks.